to 126. So we can start, I guess. All right, so welcome from my workshop. We're sitting in my workshop, and so I'm going to show you certain things which I use quite a bit. So the first thing that I want to show you is this relay. Okay, are you able to see this relay? Let me turn on Wi-Fi. Are you able to see this relay? Hello?
Yes, sir.
Yes, this relay
Yes, sir.
is so big, sir.
Huh?
So this relay is so big. As we seen as like previous class,
Yeah.
it was very short.
No. So yeah, you might have seen the small relays, but this is a big relay, as you've correctly pointed out. And this relay is typically used in servo stabilizers. So there used to be a time where, not there used to be, they're still used. So servo stabilizers are used for stabilizing the incoming voltage. So if you have a drop in voltage like 170 volts or 250 volts, or a rise in voltage like 250 volts, so the servo stabilizer output will remain locked at 230 volts or whatever you set it to be. So this is one such relay. So this is the primary coil, this thing that you see. Okay, this is the primary coil, and if you observe, there is a gap between the two legs. I mean, there is one copper terminal over there, right? So when this is energized, you see all the spring mechanisms that latch. So the coil will pull one part towards it, thereby actuating whatever secondary circuit it has to actuate. Okay, so this is the coil that's gonna give the electromagnetic force, and it is made by Eagleman. It's a very famous company. All right, so you can actually remove the coil, you can service it, no problem. When you let go of the current, the spring tension will bring it back, this spring that you see over here. Okay, it will bring it back to its normal position. So normally there is no contact between this point and this point. And the fact that the terminal is quite large, it indicates that it handles a lot of current. But despite the secondary handling a lot of current, the fact of the matter is the primary does not handle a lot of current. Okay, let's see how much current the primary handles. So let me just bring the table lamp like this. So it says if you can see this, it says that the primary is rated for 12 volts and the coil resistance is 60 ohms. So how much is the current that is going to pass through this, the primary?
0.2.
So 200,
Milliampere.
so 200 milliamperes. So that's going to be the holding primary current, and that is going to switch a lot of amperes. These are all heavy duty. Okay, the contacts are all heavy duty. All right, so this is a big relay. This is a smaller relay. Okay, and it's made by Omron. Omron is a very famous company. All right, so can you see what is written? Can you see the diagram? Probably not. Can you see the diagram?
No, sir.
Yes, sir. It's not totally clear, but okay.
Yeah, it's. I mean, the
So
We can
plastic has
see a
gone.
coil.
white
We can see a
lines.
small coil.
Yeah, the white line. So okay,
So
so
no.
forget about it. The plastic has gone a bit turbid as well. So if you look at this, let me try to open it, and so that we can see what is inside. Okay. All right. So I've opened it, and if you see carefully, you should be able to see a big coil, and it is rated for DC 24 volts. Okay, this is the coil which is rated for DC 24 volts, and you will see that there are four parallel contacts. So this kind of relay, it can potentially switch four appliances at one go. Okay, it can switch four appliances in one go. So there are a lot of legs. So in these lot of legs, you will see that this and this and this and this. So basically this leg and this leg, they are the primary. These, there must be one common out of this. I have to look at the circuit diagram, which is painted on the top of the cover. But one of them will be common, one of them will be normally closed, and one of them will be normally open. Okay, so at a given flick of the primary, you can switch on four appliances in one go. Okay, you can switch four appliances in one go. Any doubt in this?
Excuse me, sir, can you treat it like it is coming side? The video is coming at the moment sideways.
Sideways.
So as in
I'm using my rear camera, so.
So
Sir, I
like
think auto rotation option on your phone.
maybe you
Uh-huh.
can do it in portrait mode, sir. Like you
In
can hold.
portrait mode.
Yes.
But everyone says not to do it in portrait. Like this, you mean?
Yes, sir. Now it's okay.
yes, so now it is clear.
Yeah, that's weird. So, yeah, this and this, they're the primary. One of these rows is the normally open contact. One of them will be common and one of them will be normally closed. Okay, and this is, can you see it now? I mean, it's difficult to see. Now you should be able to see the plastic.
Yes, sir. Now the reading is
Yes, sir.
visible.
Yeah, so what does it say? It's 5 amperes, 28 volt DC. All right, so the primary, you can feed a power supply of 28 volts. Max it can take is 5 amperes, after which the coil will go. And it can switch. What can it switch? It can switch 5 amperes, 240 volts AC, 5 amperes, 28 volt DC. Okay. And on this side, you have the connection.
Volts AC also.
It will work for AC. Despite it switching fast, it also works for AC. Okay.
So do we have a limit kind of thing, the frequency of the AC current and
No, AC will always, it is assumed that these appliances will be used with 50 hertz. Okay. Standard. And this is the circuit diagram. As you can see, on the bottom, there will be primary coil. So this shows the primary coil over here. This is the primary coil. And on the top, you have terminals numbered 1, 2, 3, 4, all the way to 12. Can you see that?
Yes, sir. we
Yes,
can
sir.
see it.
Yes, sir.
So what does it mean that 9, 10, 11, 12, they are the common, and normally closed is 1, 2, 3, 4. Okay. And when you trigger the primary, 5, 6, 7, 8 will be switched with 9, 10, 11, 12. So they will be connected. So 5, 6, 7, 8, they form the normally open connection. All right.
Yes, sir.
5, 6, 7, 8, they form the normally open connection. And there is a small indicator. There is a small indicator over here as well, which is connected via resistor that the primary is on. All right. So you can see that this is the movement. Okay. This movement is actuated by this coil. That movement will be actuated by this coil. All right, so this is also one sort of relay. It's used for switching 4 appliances. It's made by Omron, a very famous company. Over here, I also have another relay. It's also made by Eagleman. So what do you see over here? It can switch 2 devices. The primary is pin number 10 and 11, and it's a 12-volt relay rated for 200 ohms. So you can figure out the holding current. And the normally closed connections are what? Who can tell? The normally closed
One and
connections?
7.
1 and 7.
Yeah, so 1, 3, and 7, 9.
Yes.
1, 3, and 7, 9 are the normally closed connections. And the normally open connections are 2, 3, and 8, 9. Okay. So if ever
Four
you,
and
pardon
So
me,
what?
yeah,
5.
there are no connections. See, they might have made this for this same mold for many things. So because they want to reuse their molds and jigs, so they keep it no connection. Okay? So if you ever make such things, I mean, if you want to switch things using microcontrollers, you have to use such kinds of relays. Otherwise, you cannot switch heavy loads. So this is something I found in scrap. This is the voltage stabilizer, and what does it contain? So what do you see? What do you call this? Have you seen something like this before?
So the
You might
coil
have
in the
used it in your
middle.
school. You might have used it in your schools as well. It's a, what do you call it?
It's armature coil of motor.
No, that's not an armature coil. It is a coil, yes, it is a coil. You call it a dimmer stat. Have you heard of dimmer stat?
No, sir.
No, sir.
Okay. Or an auto transformer. In your first year electrical lab, you have not done auto transformer.
We didn't see it physically.
Oh, okay. Okay. So what happens is, depending on where this is, it will give you something between 0 volts and 230 volts. The input is always going to be 230 volts means, and depending on where this is, where the tapping is, it will give you something between 0 and 230 volts. But why is it servo? So servo is the name of the control by which it tries to always seek. So if you look, there's a motor which is connected to the tapping. So when this motor, when the voltage sense circuit senses that the voltage has gone beyond, so the servo motor, this is a synchronous motor, will switch on, and it will try to seek a position where the voltage output will remain stable. Does that make sense?
Yes, sir.
Yes, sir.
You ask questions, no problem. You ask questions.
Sir, it is also used in like stabilizers, voltage
Yes,
stabilizers.
yes, yes. Absolutely. It is used in stabilizers. Okay, so it's a AC synchronous motor, and there's a everything is done electronically. So you will find various relays and changeovers and big current limiting resistors. And the torque rating is 3 kg centimeter. So depending on that torque, they have increased the torque by using a larger gear. Okay, so can you see that?
Yes.
Yes, sir.
So the currents, the voltage output will be sensed by a small circuitry, which will tell the motor that okay, your the tapping is at a higher voltage. You please lower the voltage, so the motor will turn appropriately. The motor will turn clockwise or anti-clockwise, it will set the correct voltage. If the voltage is lower than the desired voltage, in the set point voltage, then the motor will again turn the appropriate direction to cause the voltage to be what the user demands. All right. So that is how these servo things work. Well, there are many other things in the workshop, but right now I'm going to show you where these limit switches and all work. So this is a 3D printer. Everyone might have seen it. Some of you might have printed stuff in it as well, right? Right now I'm printing something. Can you see that?
Yes, sir.
Yes, sir.
So what are the different components which are going on? So let's take a look at the mechanical components first. So what are the mechanical components in this? What are the mechanical components?
Servo motor and
No, there are no servo motors.
So there might be some rack and pinion mechanism or
So that's a good guess, but not quite. So let me break the suspense and
so
show you.
sliders.
Yeah, so this is the slider. This belt is holding the platform. This belt, this belt is holding the platform, and that belt is pulling it and throwing it. But how is it pulling it and throwing it? With the help of a stepper motor. If you look way back, you can see the stepper motor. Can you see the stepper motor?
So
Probably
is it
not.
the
Yes,
one
sir.
at the end?
Huh?
yes, sir.
Sir, is that the
So
one
the
at the
step.
left hand?
Huh? So you see the stepper motor is rotating a pulley. Onto the pulley, the gear tooth belt is attached. Where else will you find the gear tooth belt? In your automobile, the engine is coupled to the camshaft with the help of what is known as a timing belt. So the timing belt is also an example of a gear tooth pulley. Now, how does the machine know where the stage is? See, you simply have a G code. The G code is simply executed. But the machine also needs to know that right now it's at x equal to 50, y equal to 60, and so on, right?
It's
Otherwise, there is no
calibrated
way for.
initially.
But how? How does it know? I mean, suppose the machine turns off right now. How will the machine ever know?
So it might be using the encoders to determine the rotation of stepper motor.
No, that is true. But how does the machine know where to start from? Suppose the machine turns off right now. Will the machine interpret it as 00?
No, so the position at which it's turned off, it would take that as origin and it will again resume
No,
the.
but once it turns off, the microcontroller forgets where it is.
Sir, maybe there is some like probably some electric contact between the machine and this floor so that it can determine the coordinates.
So let me show you how it is done. Can you see this part?
Yes, sir.
That switch.
Yeah, so that is known as a limit switch. So what it does is it will pull the extruder head all the way to the left. So whenever the program starts, what it does is wherever it is, it will first pull it to the left until it hits the limit switch. So how does the limit switch work? So we will discuss this when we get back to the lab, to my office. Okay, so remember this. It's a limit switch. So it helps in what is called as homing. It helps in homing a certain apparatus. Okay, and you will find this kind of a limit switch for each of the axes. So this one is for the y-axis. There's a limit switch for the x-axis as well. You see this one? You see saying this?
Yes, sir.
And there is one for the z-axis as well. This is the one for the z-axis. Okay? Each of these machines has this. So this is for the z-axis. This is for the y-axis, rather x-axis. Okay, this is for the x-axis. And there is one behind for the y-axis. Apart from that, so how does the machine know what is going on? So what does the machine do? It pulls filament, it passes through this thing, and then it sort of, if you follow the filament, it goes into this extruder where it is melted and deposited. But what is this thing? This thing is called as a runout sensor. Okay, it's called as a runout sensor, and it detects whether the filament has broken or not. Okay, if the filament breaks, it switches off the microcontroller. So this is called as a runout sensor, and we will see how it can be made very easily. All right. So many of these ideas, you may think that, okay, maybe whatever we are doing is quite Mickey Mouse. I mean, nothing of this kind is used in real life, but that's not right. Okay, this is an oxygen concentrator which we had built, and it makes use of very simple relay circuits and a very simple Arduino microcontroller. You can use any microcontroller. So what does it do? The moment the circuit turns on, there is something called as a contactor, which you can look it up. There are solenoid coils. Okay, there are a bunch of solenoid coils, solenoid valves. So everything is actuated by means of the same circuitry that we had discussed. The same circuitry which we had discussed, which includes the transistor to relay circuit. Let me just wash my hands. Everything remains the same, despite you're doing something very difficult or whether you do something very easy. Not much changes. Oh, one more thing I want to show you. Let me turn on the lights. Okay, so if you look behind these power supplies, okay, you will see a bunch of 3055s. Can you see the 3055s? Well, it's, yeah, 2N3055. Can you see the transistors, power transistors?
Yes, sir.
Yes.
And you'd be surprised that the circuits are very, very rudimentary, yet they work. So it's just to show that whatever we are learning, it's not something very hypothetical. It really finds use in interfacing mechanical motion or sensing or detection to electronics. It helps in bridging that gap. So this is a resin printer. It helps in printing very small features. And in this resin printer, if you look carefully in that gap, what do you see in that gap? Let me turn on my flashlight. Can I do it? Where is the torch? Oh, the torch is disabled during this call, is it? Oh, weird. Okay. But look into this gap. What do you see?
That this left side one.
Yeah, there's a rectangular slot. Wait, let me search for a torch. Yeah, so we have a torch. Now can you see?
Yes.
So what do you see?
T and plus sign.
T and
Huh?
plus is
Sir, this is what we discussed in the previous class, but
Yeah.
we abstracted with some
yes, sir. Yes,
object
sir.
in between.
Yeah, so it's an opto interrupter.
Yes.
Yeah, opto interrupt. I didn't get the name.
Yeah. So what does an opto interrupter do over here? Let's look at that as well. Let me turn off this. So this particular aluminum element, this element, this part rather, when this stage goes down, meaning you can see that it will go down. So when it goes down, this aluminum piece will get inserted into that slot. And so the stage, this particular build platform, this 3D printing platform will know that this is now the z equal to 0 location. Without that, this printer has no idea where this stage is right now. So when you turn on this printer, the first thing it will do is take the stage, it will go all the way down, it will say that okay, now I'm at z equal to 0. Then afterwards it knows that depending on the number of rotations of the motor and the pitch of the lead screw, how much distance will it travel. Okay, does it make sense whatever I said?
Yes, sir.
Yes, sir.
So what is that machine used for?
Are you convinced that such kinds of things are practical? I mean, it's not some mumbo jumbo.
Yes, sir. Now we are able to appreciate those small things which have a good application in all these things.
It is there in many things. It is not just this few printers and this. In I don't have any open printer right now. Otherwise, I would have shown you a bunch of things going on over there. A proper printer, a page printer that
Sir,
we use in
I
our
want to ask one
homes.
thing, sir.
Yeah, yeah. Ask please.
Sir, like I don't know whether it happens in 3D printers or not, but like
Yeah.
in normal printers, what happens is like when we switch off the printer, the
Hmm.
cartridge once move like the whole length along the length, and then it goes to rest. So
Yeah, it happens in this also. It first goes all the way to one end where the limit switch lies,
okay,
so that it knows, despite the power failure or sudden stoppage, it has to go back to its original encoder position, that is 0. It needs to go back. Yes,
okay, sir.
that's what
Okay.
you're trying to ask, right?
Yes, 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 sir. So that happens
Yeah.
because of this only.
Yes, yes, yes. That is the
Okay.
same. The ideas are the same. And whenever we will discuss about this servos, I will hopefully by that time I'll get around to programming this. So we can move, you can do things with it. It's 3D printed. If you want, you can also build your own. Okay. So
So we can replace the limiting switches with opto
yes,
controllers, like opto
yes, yes,
interrupters.
yes, you can do that. And the reason it is not done right away is the cost. The opto interrupter cost versus the limit switch cost. Opto interrupter will be very precise, but it is costly as opposed to a limit switch, which is cheap but not so precise. You get the idea, right?
Yes, sir.
So
Or
yeah, any
or we
questions so
can
far? Or?
Sir, or also there could be some marker on the printing board so that it knows the position of the board with respect to origin, something like that.
Pardon me?
What if we put a marker on the board of the printing, what do we call it? A platform, so that we can
And it
know the
looks for
location.
the. Yeah, it can be done, but see, easier thing is to do it with a tape. In using a tape, you get both absolute encoding and homing. You have both in one go. For searching for a mark, you need some particular photodiode which will detect that color or that marking. If it misses the marking due to something like dust or some spill or some paint erosion or something, then it will, it will not work. So you don't rely on such optics. You just go straight with something which literally blocks a circuit. Okay.
Yeah, got it. Yes, sir,
Yeah.
got it.
And let's see next week if I can go to the central workshop or the student workshop. I can try to show you the different things that go on in a CNC machine as well. So you all know what a CNC machine is, right? At least
Yes.
know what a CNC machine is.
Yes, sir.
So in a CNC machine, as you can imagine, it doesn't work with such trivial powers. It does require three-phase induction motors, single-phase induction motors. Then it requires very high-quality encoding. You get the idea, right? Basic idea. So it requires a bunch of pneumatics. It requires a bunch of hydraulic lines. It needs to switch on an oil compressor. It needs to switch on an air compressor. So it needs to do a lot of switching. Everything is done through a common dashboard. So all the switching is still done by very simple circuits. It's done by such relay circuits. The encoding is done by means of a very big stepper motor. This spindle is rotated by means of a very big three-phase induction motor. Three-phase induction motors can also be switched on with the help of a single relay. But after the relay, you have to also connect what is known as a contactor. So a single phase primary can also switch three-phase RGB or RYB and a neutral point. You know about three-phase, you might have learnt it in your first year electrical lab, three-phase induction
Yes.
motors. So you know about the star delta connections,
Yes, sir.
Yes, sir.
the starter
Yes, sir.
configurations. So there are circuitry which can automatically shift from a delta configuration to a star configuration. Okay, all of that is very simple to do. If you understand the circuitry, how much ampere something is pulling, whether it should pull that, whether it will get damaged. So people have done this iteratively over the years. So now they know. But you also are in a position to know, given whatever we have seen in these weeks. You now have the basic idea, or rather, you should sort of feel that yes, you have the basic idea of how to go about switching this thing. Oh, one more thing I wanted to show you. This is something which we just attached yesterday. So it's a Raspberry Pi which is connected to the internet, and the switching to my lights are done to the board. Okay, so it's a relay board, and the relay board, it contains the same optocoupler transistor circuits. It contains the same optocoupler transistor circuits. So right now the Ethernet, rather the local area network is turned off. But due to this, what I can do is I can use my mobile phone to switch on and off my lights, the room in my lights. And this was installed here by Shrey Verma, who is in his 4th year, so he's quite senior to you. But we've worked together on many things, and kudos to him. So it actually works. I switched off this local area network at the moment, but I can assure you that it works. Okay, so the circuits are usually pretty straightforward, pretty simple, but yeah, you just need to figure out how to integrate that circuit with a mechanical circuit. Okay, so there comes the whole planning for the mechanics. So you know that a certain motor gives you certain amount of torque, but your application requires you to have a larger torque. So what do? You use a gearbox, or you know that a certain motor rotation has to be converted into linear actuation. How do you do that? You can simply connect it to a lead screw and the nut. Whatever I'm saying, does it make sense?
So can you repeat the last thing which you said?
So you use lead screws. You might have seen a lead screw on a lathe, for example.
Yes, sir.
So now when the lead screw is moving, you don't know how fast or how slow it is going. So you use some kind of encoder to figure out that, okay, it's going this slow or it's going this fast or it is at this position. Okay.
Sir, are
Yes.
you speaking about rack and pinion or something?
It need not be just rack and pinion there. It can be rack and pinion, no problem. It can be rack and pinion also. There are stages on retrofit lathe machines which directly attach the motor to the pinion that you actually rotate by hand. Okay, the pinion that you actually rotate by hand, that a motor can also do. But what is the issue? The motor does not know when to stop. So what do? You somehow sense where the stage is at this moment, and then you tell the circuitry to tell the motor that, okay, now we have reached the position till which we needed to do the cutting, and then you turn off. Okay. Towards the end of the class, I will show you some of my attempts also at some of these things. All right.
Yes.
So let's just take a quick break before we continue with the 555 circuits. And trust me, these circuits are very ubiquitous. They are used at many places. So it is worth your time to just look into the additional reading material that I have uploaded on the Teams. It will only help your cause if you're ever interested to do robotics, or if you're interested to do embedded, such kinds of things. If you're doing it, is worth knowing all this thoroughly. In that case, you are in a good position to tinker around very efficiently. Okay, so today's agenda will be to wrap up the 555 circuit and to look at how a 555 circuit gives a PWM response, a pulse width modulation response, and how we can create a motor driver with the help of a transistor, a PWM circuit which is made using a 555. All right, we will see how it can be done as well. In the next class, we will see how to make an edge bridge controller. We will see how to control servos, all these kinds of things. And then we will slowly move on to operational amplifiers. All right, so we will take a small break now. So I'll be back. Join on my PC also. Till that time, you should think about the different doubts. Okay. Yeah, hello.
Yes, sir, you're on.
Yeah, so I'm in the workshop and just want to show you how the relay action works. So here we have a relay. Okay, I mean this is a solenoid coil, but you can imagine that this hand is connected to the contacts, which will actually pull the contact to the normally open connection. So right now, the spring, the small spring will cause this lever to maybe touch the common and the normally closed connection. The normally open connection will be open when this limb is pulled by the magnet like this. Okay, so now let me give it 12-volt supply. You see, it got stuck. When I release the voltage, it gets open. I'm energizing the coil, switches on, switches off, on, off. Okay, now is the action of the coil clear? So this is just the primary. So once this lever will pull the contacts between the common and the normally open connection, it can switch any kind of load depending on what the quality of the contact is. Okay, is it clear?
Yes, sir.
Yes,
So
sir.
what is the fundamental principle behind the working of this relay? What will you say if someone asks that?
Induction.
What is the principle?
Sir, electromagnetism.
Electromagnetism.
Electromagnetic induction, right?
Yes, sir.
Now I have another device which is basically a coil. This is just a coil, and we have two aluminum cylinders like this. Now it's simply connected to mains voltage. It's giving AC mains. I'll switch it on. Oh, it's not the switch. You see what's happening? What do you see?
Rotation of this aluminum cylinder.
You see rotation of the cylinders. So
Opposite
why is
directions.
it, why is it happening? Why does that happen?
So the coil is rotating the screw in between, and that is
Now the coil is
grooved.
rotating nothing. It's a fixed coil. It's rotating nothing. Everything is fixed. Everything is fixed. I'll switch it on again.
Maybe due to some magnetic field which is produced by this coil.
So it is your task now to figure out why this happens. Okay. And let me show you another thing. So this same setup, we've modified it to stay vertical as well. So I'll make the coil vertical like this. And I have an aluminum washer. So I have an aluminum washer and I'll put it in the bolt like this. And I'll again switch it on. So what do you see? What do you observe?
It wants to get out of it.
It wants to get out, but it's effectively levitating, right? It's effectively levitating.
Sir, is it because of the magnetic force?
I'll switch it off. So it touches the base. When you turn it off, it touches the base. When I turn it on, it starts levitating. Okay. So as you can imagine, rather, you shouldn't have to imagine. It's all because of something. What is that something? You will think about it. You have learnt it in class, whatever.
Sir, you're not audible.
Sir, you're not audible.
So you are not audible. And screen is also stuck.
Yes, sir.
Yeah.
No,
So yeah, I mean, I think I lost connection for a while. So yeah, this is an old lathe we have, and this is all the control circuitry to make this lathe operate. So you can see that there's a bunch of stepper controllers. We will look at this stepper controller business in one of the labs. But essentially that stepper motor controller is connected to the stepper motor over here. And when the stepper motor rotates, you can see that it will also cause movement of the stage. Okay? It will also cause movement of the stage. So there is one for the transverse movement, and there is one stepper motor ball arrangement over here for the movement of the stage. Okay, right now I'm doing it by hand, but otherwise it becomes computer controlled. So essentially you can sort of retrofit things and make everything computerized as per a desire. And this big thing that you see over here is known as a VFD. It's a variable frequency drive, which drives this motor at variable RPM and which rotates the chuck. Okay. So that is how you can sort of go about retrofitting things. So this is something which I attempted just for my free time, nothing else. So this is a small tabletop milling, and even that has the same kind of control. So it has a stepper motor, and it causes movement of the stage in the X direction. And there is a stepper motor for this base as well. It causes movement in the Y direction. And there is a small lead screw over here, which causes the tool to go up and down. Okay. Let me just wash my hands. All right, so now we're back to the PC. We have gone from the workshop. I hope you found all that interesting, and hopefully you will. Yeah.
So that earlier that levitation was caused by eddy currents, I guess. Like, eddy currents like generates this like there will be magnetic force.
Yeah. It's eddy current, but the primary thing is electromagnetic induction. All right.
Yes.
Even the first thing that I showed was electromagnetic induction. Nothing else. There's no magic going on. I mean, that's just made to show people what electromagnetic induction can do. All right. It's nothing that is not to do with mechatronics, but I just wanted, because I showed you a relay coil, a solenoid coil. I just showed how electromagnetic induction manifests itself in other forms as well. All right. So if you have any doubts, you ask me right now before we move on. And whatever we did in the previous classes. No? Okay. Wait, so this recording, it has started from the starting, or the earlier recording was saved? Or it was saved, right? Oh.
No, sir, it's the same recording continuing.
But for me, it shows. Okay, maybe it shows the join time. I switched devices. So maybe, I don't know. I hope it's recorded. All right, so let me open up journal and then we can proceed with the discussions where we were in the last class, in the last lab. Let me know if you can see the screen.
Yes, it's visible.
All right.
Yes, sir.
So in the last class, we had discussed the two modes of operation, that is the monostable mode, and before that we had discussed the bistable mode. Okay, we have discussed what the any 555 circuit does, and so you can have it hold an output for a certain amount of time, like so. Okay, you can hold it for a certain amount of time, or you can have like a soft switch. Both of these have been discussed. If you don't remember, or you can always go back and look at the recording, no problem. Lastly, we will come to the more useful, I mean, the previous ones are also useful, but here we will discuss about the astable oscillator, which is also used in many circuits which pertain mostly to motors. So what do we have over here? We have, so you may find it a bit disorienting because we are suddenly starting from a circuit again, but just bear with me, just try to remember the basics, that there is a VCC pin, there is a trigger pin, there is a threshold pin, there is a reset button, rather reset pin, and there is a discharge pin. These things you must remember, and there's finally an output. Okay, so whatever we had done previously was basically to somehow manipulate how long the output remains on or off. And so we used a bunch of switches. Okay, in whatever we discussed, we used switches, but you don't want to always use switches to find some kind of waveform. So this particular circuit, it does not make use of any switch, rather it makes use of two resistors and a capacitor. So let's call this C1. It makes use of two resistors externally connected and a capacitor. All right, and you still have all the other circuits where, while this capacitor voltage is tied to both pins 2 and 6. So what are pins 2 and 6? Let's just take a look. Pins 2 and 6 are the trigger pins and the threshold pins. All right. So what do we see? We see that VCC first goes between resistances R1, R2 to ground, and the moment this is connected, it starts changing the voltage at this point because the capacitor starts to charge, and you have R1 and R2 kept as a voltage divider, but we are not using R1 and R2 as a voltage divider, but the tapping of R2 is used to discharge, nothing else. Okay, so whenever the capacitor discharges, whenever the capacitor will discharge, it will discharge across what? Look, this is the discharge capacitor, discharge transistor. when discharging will take place, the capacitor will follow this route and it will discharge to ground. Okay, but how does the capacitor charge? What is the line through which the capacitor charges? It is charging through resistances R1 and R2. All right. Is this much clear?
Yes, sir.
All right. So now let us take a look at the sequence of events that happen in this mode. Okay. So the first thing, the capacitor starts charging immediately. So let's see what happens. So the first phase will be the capacitor is charging. Now during this charging, the voltage at the capacitor, which we have denoted by VC, it will initially be 0. So because the circuit is just connected, it will be at ground. So the capacitor voltage, that is VC, which is essentially the voltage at this point, it will be less than 1/3 VCC. This is VCC. It will be immediately less than 1/3 VCC. So when VC is 1/3 VCC, let us take a look at what the comparators now output. This is comparator 1 and this is comparator 1 and this is comparator 2. So let's see how this happens. So for comparator 1, the inverting voltage is 2/3 VCC, whereas the non-inverting input is something which is definitely less than 1/3 VCC because the capacitor is in the process of charging. So it is definitely low. So the output of the comparator will be what? The inverting pin is at a higher voltage and so the output of the comparator will be 0. What about the second comparator? Again, the inverting pin is at VC, which is definitely lower than 1/3 VCC, whereas the non-inverting input is at the reference voltage internally set, which is 1/3 VCC. What happens then? The output of the second comparator. Here, the positive pin of the comparator is at a higher voltage, and so the output of this comparator will be what? The positive pin is at a higher voltage. In that case, what will be the output? Am I audible?
Yes, sir.
So this positive input is larger than the inverting input. So what do you get? You get a 1 signal, right? You get a
1.
high signal. Yeah. So you get 1. So in the RS flip-flop, the set pin is at 1, meaning Q will be equal to 1. This is Q and this is Q bar. Q becomes equal to 1 and Q bar becomes equal to 0. And once it goes to the output inverter, output will become equal to 1. Okay, so when the capacitor is charging and the voltage at the capacitor is less than 1/3 of VCC, the output will be high. All right. After this, what will happen? The capacitor is still charging. See, because the Q bar output is 0, okay, and the output is 1, nothing happens. Okay, you still have the capacitor charging. Now capacitor charge will go to this position. It will go to a position where it is greater than 1/3 VCC and less than 2/3 of VCC. In that case, what will happen? Just follow this. So for the first comparator, it is still less than 2/3 VCC. The first comparator is always trying to compare against 2/3 VCC. But because the capacitor voltage is less than 2/3 VCC, the output still remains low for the first comparator. But now for the second comparator, the output voltage of the capacitor is now larger than 1/3 VCC, meaning the inverting pin is at a higher voltage than the non-inverting pin. So what does it mean? That S, which was originally 1, has now become equal to 0. But when both R and S are at 0, there is no change in the output of the RS flip-flop, and so Q stays at 1, Q bar stays at 0, and so the output correspondingly remains high. Now what is the next logical step? The capacitor charges to a voltage larger than 2/3 of VCC. When the capacitor charges to a voltage larger than 2/3 of VCC, what will happen? Now this capacitor has charged to larger than 2/3 VCC. It means that this positive pin of the comparator has gone larger than the negative pin of the comparator. What will happen in that case?
The
So
output
it
of
will become
competitor one
1.
changes. 1.
So the output of the first comparator will become 1, but because the VC has grown to more than 2/3 of VCC, then definitely still the inverting pin is at a higher voltage, right? So
Yes,
the
sir. So no
output,
change.
so there will be no change in the second comparator. It stays at 0. So because the reset pin is at 1, the RS flip-flop R pin is at 1, meaning it resets. So now what will happen is Q will become 0, correspondingly Q bar becomes 1, and the output is 0. Once the Q bar becomes 1, the transistor becomes on. Okay, the Q bar is fed to the base of the discharge transistor internally. You don't have to make this connection. So Q bar becomes 1, and so this particular uh, discharge transistor becomes on. Now what will happen? Now the capacitor sees that I have a discharge line. What is the discharge line? We have discussed it. It is this line. It is this line which is now the discharge line. It can discharge through the discharge pin to ground. And so what happens? So the discharging of the capacitor happens from C1 to R2 to ground. Okay, this is how the capacitor will discharge. That is C1 to R2 to ground. All right, this is how it will discharge. So once it discharges, what will happen? The capacitor will again go to its base state, which is 0, and then the whole cycle will repeat. Okay, the whole cycle will repeat. So what does it mean? What can we conclude about this? Capacitor charges across R1 plus R2. This is the charging line. Capacitor discharges only between R2. This is the discharging line. And during the charging line, the output remains high, and during this time the output remains low, after which it again becomes on, then off, then on, then off. So this time which is 0.7 times R2 times C1 is the off time, that is the discharging time. This time, which is the charging time, what will be the charging time?
R1 plus R2.
Yeah, so 0.7 times C1 times R1 plus R2.
R1 plus R2.
So this is the on time, this is the off time. With the help of this, you can obtain a sawtooth profile.
Sir,
Okay.
but like, wouldn't it switch immediately? Like, as soon as the capacitor voltage is more than 2/3 VCC, it will go into the discharge mode.
No, it will not go, because there will be a state where there will be no change. It will go to 0, 0. So I request you to keep doing this all the way to the end, but you will obtain this mode in between and there will be no change. Okay. You do it. You just go ahead and do it. All right. Or you figure out how this will work. I mean, I've told you the basics. We have discussed the basics in the previous class as well. You just do the basics. Oh, no. Actually, you're absolutely correct. It will go back to this state from it will go to no change. Yeah. Then again, between 1/3 and 2/3, it will keep oscillating. Okay. So it will keep oscillating between 1/3 VCC and 2/3 VCC. So you can figure out the charging and discharging time. So it will not be 0.7, it will become 1.1. You try to just figure out using basics of what you learned in your first year. You have to do that much. because it's not going all the way to VCC. So your small task will be to superpose how the capacitor voltage will look on this plot. Okay, how the capacitor voltage will look on the same plot. So here we have plotted the output voltage. I have not plotted the capacitor voltage. So you should try to figure out how the capacitor voltage will look on the same plot. All right, and you will find the same profile in many of the links that I have shown. So now,
So by that logic, the first part of the sawtooth would be higher, wider than the other parts, right?
when it immediately begins, that first part will be larger. You are correct. But once it goes into the astable mode, it will become fixed.
Okay, sir.
Only the very first time this extra 1/3 VCC charging will stay extra. That much time it will stay on extra. Do you understand? That was your question, right?
Yes, sir.
Good. Very observant. So yeah, so instead of doing this circuit, there is another way of getting this done. So in the previous circuit, what did we do? We have VCC, then we have this way of doing it, and this went to the discharge line. So you were charging like this and discharging like this. So in both of the expressions, for the charging and discharging time, you have always had this R2 in picture. You always had R2 in picture. But see, I mean, typically in this application, R1 is kept small and R2 is kept large in this application. So you will see that when R1 is much smaller than R2, then approximately this expression and this expression, they are equal. So you will obtain a pulse which is on half the time, which is off half the time. So you will obtain what is known as 50% duty cycle. Okay, you will approximately obtain something which stays on half the time and something which stays off half the time. So it is on half the time, 50% of the time, it is off half the time, which is 50% of the time. So the duty cycle is 50%. Okay, it is the on time divided by the total time. This duty is the on time divided by the total time. But suppose you don't want to do that. So what do? So you have R1 over here, and again you have a large resistor over here, R2. But now R2 is a trimmer, meaning R2 has 3 legs. One leg, other leg, and a middle leg. And suppose this says 5k ohm. Okay, it's known as a trimmer. So across this leg and this leg, if you measure the resistance, you will obtain how much? You will see a resistance of 5 kilo ohm. But there is a small screw on top. You can rotate the screw on this axis. So internally, if the screw is rotated, you will obtain a fraction of 5 kilo ohm across this and the other fraction across this. So if X is the fraction coming out of between these two terminals, so let me just color it differently. So between these two legs, you will obtain X times 5 kilo ohms, and over here you will obtain 1 minus X times 5 kilo ohms. So if X is 0.2, if you rotate the screw, then if X is 0.2, how much resistance will you obtain in this leg between these two terminals? Just multiply 0.2 by 5. How much do you get? 1 kilo ohm, right?
1 kilo.
And correspondingly between these two legs, how much will you get?
4 kilo ohm.
4 kilo ohm. So it is similar to what the potentiostat experiment that you might have done in your school. Do you recall such an experiment, a potentiostat? Do you recall such a thing?
Potentiometer was there.
Potentiometer, not a okay. My bad. You used a potentiometer, right?
Yes, sir.
So you had one terminal coming in, then a coil like this, and then a tapping. That tapping was moved from left to right, and another terminal over here. So it's the same thing. When you move this, you are essentially changing the resistance between this and this.
and the complementary resistance will appear between this and this. Okay, it's the same thing. This trimmer does the same thing. Okay, so now what is the deal? So if this is x, so if this fraction is x, this fraction becomes 1 minus x of R2. So the charging circuit, because of the arrangement of the diodes, so the charging, during charging, current flows like this. It goes through R1, then it flows through this diode through this x times R2, and it charges the capacitor. So the capacitor charging is R1 to x times R2 to capacitor. And how is the discharging happening? The discharge line is what? The capacitor to 1 minus x times R2 to discharge, right?
Yes, sir.
So in that case, the charging time is approximate. See, R1 is going to be small, so charging time will be approximately x R2 C1, and the discharging time will be approximately 1 minus x R2 C1. And so, depending on the position of this small screw, you will obtain the same total time, which will be R2 C1, but you can now change how much time. You can now change the on time and off time accordingly. Okay, maybe this is like a 10% duty cycle. When you rotate the screw so that x becomes equal to 0.5, when x becomes 0.5, it will become like this,
50% duty.
50% duty cycle. When x becomes 0.7, maybe it becomes something like this, and so on. Okay, so therefore you have a way of generating pulses. Yes, you have a way of generating pulse width modulated response. Okay, you are generating pulses. The frequency maybe is 1 kilohertz. Suppose that the frequency, this frequency is 1 kilohertz, and in that frequency, suppose you are working with a 70% duty cycle or a 0.7 fraction, then over that entire time, if you average the voltage, so when you have a 70% duty cycle, what is the average DC voltage that you will see? If the output is VCC, or let's simply call it V out. If the output is V out, then for a 70% duty cycle, what is the average DC voltage that you will observe?
0.7
0.7
V
V out.
V out.
0.7 V out. Very good. So this is the basic idea of pulse width modulation. This is the basic idea of a pulse width modulation. All right. So any doubts so far?
Hello, sir.
Yeah.
Sir, the astable case, like during the first charging, so the pulse will be more wider than the other case,
Yes.
the continuous, right?
Yes.
Because one third will be
correct,
like remained throughout the
correct.
cycle.
That a very initial, that very first pulse will be wider than the others. You are absolutely correct.
Thank you.
Unfortunately, I can only see your abbreviated names like ER, MS. I don't know who you guys are, but these are good questions. Good. Some voices I can recognize, but if everyone says something, it will be better. But you get the basic idea. You now know how you can do it. Do you understand why these transistors are required? Why these transistors are required? Not transistors, diodes are required.
Yes, sir.
This
Yes, sir.
diode and this diode.
So I just wanted to ask, so
Yeah.
then why is it that we are using both the fact that we are using two resistors as well as the diode thing. Like, can't just using one be enough to do the modulations?
The other resistor, the utility of the other resistor, I am also a bit unsure about it. This first resistor R1, I am also a bit unsure as to why they put it in line. But ideally, you can directly connect VCC to this circuit. It should still work. I mean, the sort of demo circuits that they suggest, the datasheet suggests, it says to put this R1, despite this R1 not actually being connected to anyone. Oh, no, 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 I know why it is there. No, 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 no. Hold on. Anirudh Bajaj wanted to ask something, but before that, who asked this question? MS is who? Manish Singh, right?
So Mayank
Mayank Srivastav.
Sinha.
Mayank Sinha, okay. I guessed. So suppose this resistance R1 is not there. Suppose this resistance R1 is not there, then what will happen? What will happen? You tell.
Our source voltage will also get discharged.
No, no, no. So when the discharge happens, see, when the discharge happens, this ground pin, this transistor becomes on. This transistor becomes on. So this ground voltage is approximately here also.
Okay, sir. So we'll have a short
No,
circuit.
no, no. So VCC will become shorted to this guy. VCC will directly get shorted to ground.
And we'll have a
And
short circuit.
yeah, so internally the discharge pin will experience a short circuit. It will become very hot. So this R1 is always kept in circuit as well.
Okay, sir.
There you go. We applied our heads and we have the answer. Good. Is it clear to everyone? Not just Mayank. Hello?
Yes, sir.
Yes, sir.
Perfect.
So you said that R1 is very small, then the current would be very high in this case, right?
Yeah, R1 is, I mean, when I say very small, I mean something like a 1K, 1 kilo ohm resistor.
Okay.
And R2 is kept like 10 kilo ohms or something. Okay? I mean, very small is, I mean, relative term. It is kept relatively small to R2. Let me put it that way. R2 is relatively small when compared to, rather, R1 is relatively small when compared to R1. Okay? Typical values R1 will be 1 kilo ohm, R2 will be 10 kilo ohm, something like this. Or even it can be 100 kilo ohms also. In fact, in the sample circuit that I have, I think it is 100 kilo ohm. So far so good, no doubt. Everyone is happy.
Yeah, yes, sir.
Yes, sir.
So now give me a bit of time to rearrange things so that I can show you the circuitry. I need to set up my office again. So just give me 5 minutes. Don't leave the meeting. Okay, I'll be back. Yeah, hello. Where is the power supply? One moment. Yeah, we are now set. Okay. Yeah, am I audible?
Yes, sir, you are audible.
Okay, okay. So last
Sir, it would
class.
be helpful if you unshare your screen on your PC.
Oh, it is still shared, is it? Okay, one moment.
Yeah.
And now someone needs to spotlight. Let me spotlight myself. Is it okay?
Yes, sir, it's spotlighted.
Okay, so for this we have our portable DC power supply, and we'll start with the the setup which we had last class. So let me see if I can. This is going to ground. So I need a jumper wire. Do I have a jumper wire? I mean, I do. Oh, I have a jumper over here. Okay, one moment. I don't want to disturb this. Wait a moment. Yeah. So we need to probe the capacitor voltage, right? So let me connect a jumper over here so that this is the capacitor voltage. And I need my second probe. Just a moment. Yeah. Okay. So let me switch on the oscilloscope. Let me connect the second probe. Okay, so quick calculations. So let me check first the resistance. The resistance R1. So R1 is 1 kilo ohm. Are you able to see it on the multimeter?
Yes, sir, 0.98.
Yeah, so it's 1 kilo ohm. And this is 10. What is it? 3 part number. It is 10 kilo ohm. If I remember the codes correctly. One moment. Yeah, it is 10 kilo ohm. No, sorry, it's 100 kilo ohm. So this blue thing over here is 100 kilo ohms. Okay. I cannot put the probes because it has been sort of glued in, because it is very easy to pop out otherwise. This blue thing over here. Okay. If I don't glue it in, there is a tendency for it to come out. So that is 10K and everything else. So capacitance I will not measure. I will tell you the value later on. Let me just get rid of this multimeter for now.
So this blue thing is R2.
Yes, the blue thing is R2.
So
Okay.
you have discussed about that trimmer kind of thing which has a knob
No,
which rotates.
Yeah, this is the
that
knob.
that?
This thing is the knob.
Okay, yes, sir, it's visible here.
But I am using pardon me. I am only using two legs of this as the resistance. See, R2 in that circuit is ideally fixed. This is not the second circuit. This is the first astable circuit that I'm discussing. So typically R2 would be a fixed resistor, but here I want to show you how the time constant will sort of change things around. And so I'm using a variable resistance. I'm just using two legs of R2. I'm not using all the three legs of the R2. Okay? That much is clear, right?
Yes, sir.
Okay. All right. So now let us connect it to the power supply.
Art works like a rheostat.
Yeah, it does work like a rheostat. I called it potentiostat by mistake. Remember in that lecture, I mean, during that lecture, I called it potentiostat by mistake. It's a rheostat. Okay, so now let us probe the output with respect to ground. So this is ground and this is R2. I have not switched on the circuit yet, so we will not see anything on the oscilloscope. Is this trace visible? Yeah, I think it is visible. So let me switch it on. Right now it is at, okay, so you see this waveform?
Yes.
And now when I tune, so let me just trigger it so that it stops moving. Okay, now it's triggered, so the waveform is frozen. Okay, now let me just tweak this resistance. You see how it's shrinking? I'm just rotating it. You see?
Yes.
Yes, sir.
And what do you see? It's 50% duty cycle. It's 50% duty. It is on half the time. It is off half the time. Okay, so it's 50% duty cycle. I think I need to switch on. Yeah, I think it is okay. Sort of make it. It's 50% duty cycle, right? I don't know.
So we
This
are
is
able
50.
to
Yeah,
zoom.
okay. I cannot zoom in. So now, I mean, this much is clear. So this is the first circuit that we discussed, and we did say that it's going to be 50% duty cycle. And so now let us probe the capacitor voltage. Let me use the second probe. Let me use the second probe.
Sir, just now you're changing the total resistance, right? When it's like shrinking and zooming out.
I am changing R2 effectively.
Okay, yes, sir. Yes, sir. R2.
Yeah. So now let me connect.
So like you're changing the total value of R2 or just the X?
No,
The
just
total
X.
value.
I mean,
So then that
here
should
because
change the duty cycles, right?
no, in the first circuit, everything is happening via R2 only. You recall the first circuit. everything is happening via R2 only.
Okay, sir.
Yeah. So I mean, I have no means to change R2. I cannot sit down with a bunch of resistors. So I used only two legs of R2. I used only the middle leg and one of the end leg of R2 of this trimmer to get the job done. Is it okay? Does it make sense?
Yes, sir. Got it, sir.
All right. So now I'm gonna connect the capacitor and I'm gonna switch on this as well. Wait, am I not probing the capacitor voltage? I am. I am probing the capacitor voltage. Where is it?
Sir, I didn't get why after rotating the waveform was shrinking.
I'll tell you. Let me go back to the PC and I'll tell you. Why is it a flat line? Capacitor. Oh, sorry, I needed to probe it with something else. This, okay. Then we now have the capacitor voltage as well. And let me just magnify the voltage. Are you able to see this voltage first of all? This is the capacitor discharge charge business that is going on. And let me switch on 2 as well. So are you able to see this? I don't know whether you will be able to see.
It's visible, sir.
Okay. The purple one is visible as well?
Yes, sir. Both are visible.
Okay. So as we can see, the on and off, they correspond to the capacitor voltages jumping around as well. And the capacitor charging is like a arc up and it's an arc down while discharging. Okay, so are you convinced now that it is that circuit that we showed? Or are you still not convinced?
Yes, sir. Convinced.
Yeah, this should be better. Okay. Fine, everyone, not just Venkat.
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
perfect. So now, if you agree, we will move on to the next circuit. That is having the two diode arrangements for discharge and charge cycles different. Okay. So any doubt in this, you ask. Whatever you want to ask, you ask. No problem.
So here actually I don't understand the thing. When you change the R2 value, or you didn't change the R2 value. Like
No,
where?
I'm changing the R2 value. I'll change it again. I'm simply going to reduce the R2 value. Are you?
So sir, duty cycle is remaining 50% only.
Yes, duty cycle will remain 50%.
So is
See,
duty cycle like not depending on the value of R2?
no,
Like
because in the first circuit, I told that the charge and discharge times they are R2 times C1. Because R1 is much smaller than R2. R1 is 1 kilo ohm and
it's
R2 is
okay.
10 kilo ohm.
So
100
that's
kilo ohm.
why it is not depending. As
Yes.
R1 is very less. Okay, sir.
But only
That's
the
it.
frequency is changing. See, only the frequency is changing.
Yes, sir. Yes, sir.
See, only the frequency is changing.
And so if R1 is comparable to R2, then there will
Ha.
be change, no?
Yeah. Then there will be significant change. You are correct.
So here by
The,
rotating,
yeah, I'm
X
rotating.
will change, na?
Yeah, X is changing.
How R2 is changing.
I mean, okay, R2 is the value I'm sort of telling as X times R2 is what I'm calling as R2. The resistance in the circuit that I have shown. Come on, guys.
Oh yes, sir. Sorry.
I think you are just nitpicking at this point. This R2 I'm changing by using two legs of a trimmer. I am using only this as the resistance, and this resistance, instead of calling it 1 minus X times R2, I am simply calling it as this R2. We are discussing this circuit. Oh, I am spotlighted, is it?
Yes, sir. You are spot.
I
It's
need to.
visible screen.
No.
So this screen,
I want to show the computer screen.
yes, sir, screen is visible.
Okay. So this is what I'm referring to as R2. This variable, I've used a variable resistor in place of this R2 because I want to show you that changing R2 does cause the changes. So this R2 I'm changing by rotating this screw.
Sir, at this point, rotating the screw would change the frequency, but
Yes.
and not the PWM. But when we make the PWM like controller circuit that you had showed, changing the like rotating the screw would change the PWM and not the frequency, right?
Correct. And I
Okay.
will show you that. I'll show that as well. You're correct. So I'm gonna unshare my screen right now. So I should still be highlighted. What do you say? You see this, right? I mean, everyone is convinced that it's the capacitor charging, discharging, which controls the two peaks, the on and the off, the plateaus rather, not the peaks, but the on and the off is controlled solely by the capacitor. So let's move on. I think everyone has understood this thoroughly. So let me remove the probes. I have removed the probes. And let me replace the circuit with the PWM circuit. So in the PWM circuit, are you able to see this circuit?
Yes, sir.
So what's going on is, where is
Sir,
that?
it's out of focus. Focus
It's
is.
out of focus now.
Yeah, sir. Now it's a bit better.
But where did I keep that screwdriver? Wait. Did I put it in my pocket? Okay, where is it? Oh, here it is. No. Is it below? Where is the screwdriver gone? Wait. Yeah, okay. So in this circuit, this is the diode 1N4148. The part number is 1N4148. So this forms the diode network. This is the R1. This resistance is R1. This is R2. Okay. And so finally what I'm doing is, and you should be able to figure this out on your own, I'm driving a DC motor. This is a DC motor. And the output is fed between the two legs of a transistor. Okay. It is, the output is being taken between the collector emitter of the transistor. I'm using switching. So using the output of the 555 circuit, I'm feeding to the base of the transistor. This is the transistor. This metal cap is the transistor. I'm feeding the output to the base of the transistor. So what is happening? When the 555 is giving an on signal, the transistor collector emitter line becomes on. When the output of the 555 circuit is off, then the transistor is also off. But because it is happening at such a high frequency, at a kilohertz frequency, the motor does not have enough time to sort of show you that the power supply is off. Okay, but on an average, it will receive a reduced voltage, like we discussed. Okay, when the duty cycle is 70%, then the motor will see that I am only getting a smaller voltage. It will not like move on off on off on off on off. A motor has enough inertia to not do that on off business. That inertia we are exploiting to change the speed of this DC motor. Okay, we are exploiting that inertia to sort of tune this X factor of R2 to change the duty cycle that eventually switches the transistor very fast, and effectively we will see that the speed of this DC motor will change when I change R2, rather the X of the R2. Come on guys, you really did a number on me because of that X. Is that clear? So I'm gonna connect the circuit. I'm gonna make the connections. Connections are done. I'm gonna switch it on. And what do you see? You see that this is rotating. Like I'm pretty sure you will not be able to see anything solely because the team's transmission will be slow and whatnot. But the motor is rotating. Are you able to see it somehow?
Yes, sir. We
Yes,
can
sir,
see
it
the
is
rotation of
visible.
that
Oh,
blue colored
yeah, the blue colored.
pointer.
Yeah. So now I'm gonna change. Can you hear that the speed has reduced? Let's go to very low speeds. Then it will be very obvious. This is a lot of turns. So this screw has a lot of turns. It's not just like you make one small rotation and everything stops. It has a lot of turns, so it takes a bit of time. Can you see that now it is rotating very slowly and you can clearly see that inertia business. Can you see?
Sir, it is better visible on the
Yes,
LED
sir.
that is blinking slowly.
Okay, yeah. You can also see it through the LED. That is the
Yeah.
purpose I put the LED. So the LED blinking. Yeah. So it's blinking slowly. So it means you have really reduced the duty cycle, like anything. And the motor itself is like, you can see that inertia is not able to cope up. Okay.
Yes, sir.
So now let us probe the signals. You have seen this. Let us probe the signals.
Sir, I just wanted to ask, like, using this, like, we are able to control the speed of the motor, but like, wasn't it introduce unnecessary acceleration and deceleration of the motor?
When the frequency is high, that doesn't really come into the picture. But ideally, I mean, it should, but it doesn't come up. The torque rate characteristics get a bit compromised, but other than that, no problem.
Sir, if you are worried about that, we can increase the workload to near 70% or 80% like that, so that.
Yeah, you typically keep it high. Okay, so this is how the frequency is looking. Okay, you cannot see anything. Can you see? Okay.
Yes, sir.
So now let me rotate this screw.
So why is there empty pulse that is passing through the pulses?
That is because of aliasing. Let me just set the trigger, it will go away. Oh, where is it? Channel 2 is off. Mm. Oh, sorry. What has happened? Let's just do it auto. It has nothing to, I mean, there is no empty pulse. It's just some.
Sir, is that the indication of forming of pulse?
No, no, it is just scan going from left to right. It is just a scan which is going from left to right. It is nothing very complicated as you think it is. Okay. So now let me change the position on. So now there is no pulse going, right? So I'm rotating this screw. Oh. Can you see the PWM changing? The duty cycle is reducing. The
Yes.
speed has also reduced. The LED is also blinking slowly. Okay. Can you see it?
Yes, sir.
Perfect.
Yes, sir.
Let me now increase it. It's difficult. I have big hands and this is a very small thing. So it's difficult for me to hold this oscilloscope, do this. Okay, so now you see the duty cycle is increasing. The LED stays on much larger. This transistor you won't find anymore. It's a SL71 part number. It's a germanium transistor. Anyway, I had it lying around. You see the
Sir,
duty cycle
so
is increasing, right?
sir, so the combination of all the 555 timers is used in those decorative blinking lights.
It can be. It can be used. You can make one, no problem. Okay, so now you're able to see we are at a higher duty cycle. The LED is staying on. Motor is also rotating at a high RPM. Okay, are you convinced?
Yes, sir.
All right,
Yes, sir.
I'm gonna switch off. So let me disconnect everything. I'm gonna disconnect all this. So let me get back to my table. Okay. So yeah, I guess we can call it a day. I don't want to overload you with more information. So what are your takeaways? You can tell me. Am I audible?
Yes, sir.
Yeah. So what are the takeaways?
So first we observed all the practical application of all the basic circuits which we have discussed in the previous classes
Yeah.
from your workshop. And we also have seen the 555 timer, how to adjust the workload using the basic charging and discharging of the capacitor, and the logic of the circuit created.
Okay.
And we have practically applied that on a breadboard and have observed the variation of the output voltage on the oscilloscope.
So basically what we have done is a very rudimentary speed controller for a DC motor or any appliance. Okay. We have essentially made a variable voltage which can make any DC appliance work nicely. So what was the circuit that I spoke about? So let me just draw it before, I mean, if anyone has doubt that transistor, where did that transistor come into picture? I mean, of all things, everything was very nice until the transistor came into being. So let me open this circuit where there are no annotations. Let me just grab hold of this. Okay, so this was the circuit, right? And what I did basically was this output, I connected it to the base of a NPN transistor. Alright, and between this I connected the DC motor, and this is connected to ground. I mean, of course there is a resistor over here, this RB. I connected this to ground, and across the terminals of the DC motor I have connected a small diode, because motor is an inductive load, and this is also connected to the same VCC. It is also connected to the same VCC. So the output is switching, it's maybe giving 5 volts, so it's going switching on the base. So depending on the impedance of this motor, it's giving enough voltage for the motor to run. As simple as that. Okay, and because this is happening at maybe a kilohertz frequency, the motor does not have enough time to sort of see that it's on or off. It simply sees some reduced voltage. If 100% duty cycle sees 10 volts, and 50% duty cycle at 1 kilohertz or at some high frequency, it will see 5 volts. It will, the motor will perceive that the incoming or the voltage applied across it is not VCC. It is 50% time of VCC. If it becomes 30%, then it will see that it is 3 volts. Okay, this is how you form a voltage controller for driving DC appliances. Is that okay?
Sir, can we use this circuitry for a stepper motor?
Not this directly. For a stepper motor, there are, so if you have a, I mean, there are various kinds of stepper motors. There is not just a single stepper motor. There is hybrid steppers. Then there's what do they call it? Bi-coil, I mean, two winding steppers, single winding steppers. So this can be used for a single winding stepper motor. For the common stepper motors that you see nowadays, those are the hybrid stepper motors. For the hybrid stepper motors, you have to use two of these. You have to use two such circuits. And thankfully, someone has made an integrated chip which incorporates all that pulse generation. So that IC, I mean, if you're interested, you can look it up. We will discuss it in some future class. It's the A4988 IC.
So like that integrated chip has
Yeah.
already this
Yeah.
555
Yeah.
in circuit inside.
So I'm not sure whether they use a 555, but essentially it does the same job. Okay, it essentially does the same job.
Okay.
See, integrated circuit, it's difficult to say what, I mean, until you get all the blueprints and all, it's difficult to say. Okay, so a lot of things we have discussed. Try to make sense of the assignments. They are for your own benefit. Hopefully, you will do them with vigor and zeal.
Sir, can you please repeat the mode of submission of these cubes?
You can draw it by hand, you can make it on Falstad, put it in a report, you can make it on Tinkercad. Okay, you can use Proteus, you can use anything. The question has to be answered. I have given you like this question. So there are tasks for you, and then there are the sample questions. The sample questions are for your practice, that you understand what has happened in the class. You don't have to do those. Those are like sample questions. The tasks you have to submit in that assignment portal, whatever it is. The exam that we will take, it will have questions like those which are mentioned in the sheets. Okay?
Yes, sir.
Okay then. Thank you for attending the class, and I'll see you next week.
Thank you, sir. Bye, sir.
Thank you, sir.
All right.
Thank you, sir. Bye, sir.
Bye bye.
So just stop the recording so that
Yeah,
it gets.
yeah, stop it.